All right, let's get into it. Today, we're putting on our detective hats because we've been called to the scene of a chemical reaction. And honestly, the details are pretty thin. We've got one key piece of evidence, a couple of known facts, and a mission to figure out the hidden rules that are running this whole show. So let's open up the case file. And here it is. This is our first and most important clue. This graph is tracking the concentration of something over time. Now, we don't know what that something is just yet, but its entire story is laid out for us in this one curve. You could say every single point on this line is a footprint, a tiny piece of data that's going to help us crack this case wide open. Okay, so what do we actually know for sure? The lab report gives us this, the official equation for the reaction. It tells us that two molecules of some gas A react, and they form one molecule of gas B and two molecules of gas C. This is our cast of characters. The big question is, which one of them is the star of our graph? So first things first, we've got to identify our mystery substance. We have to figure out which one of our characters, A, B, or C, is the one whose journey we're watching on that graph. It's a classic whodunit, really. So let's get right to it. Is the substance in our graph a reactant, something that's being used up, or is it a product, something that's being created from scratch? The shape of that curve has the answer locked inside. We just have to look closely at the evidence. In any reaction, there's a really basic rule of thumb. The reactants, the ingredients you start with, they get consumed, so their concentration has to go down. And the products, well, they're what you're making, so they start at zero and their concentration goes up. That's pretty much the plot of every chemical reaction story. So if we look at our graph again with that in mind, the answer is just staring us in the face. The curve starts high, and it drops over time. The concentration is definitely decreasing. And if we check our case file, the only thing being used up is A. So, case closed on this part of the mystery. Our graph is showing us the disappearance of reactant A. Awesome. So now that we've identified our suspect, A, our next job is to figure out just how fast this all went down. We need to get a read on the speed of the reaction, right when it first kicked off. What we're looking for is something very specific called the initial rate. The best way to think about it is like the speed of a sprinter the exact moment the starting gun goes off. It's the reaction speed right at time zero, when it's going as fast as it possibly can before it inevitably starts to slow down. So how in the world do we measure that? Well, the technique is actually hidden right here in our evidence. We go back to our graph, and we draw a straight line that just barely kisses the curve at the very beginning, right there at time zero. The steepness of that line, its slope, is our initial rate. Let's just break that down real quick. First, you sketch that tangent line. Second, you just pick 2 points on that new line that are easy to read. And finally, you calculate the slope. That's just the change in concentration divided by the change in time, the old rise over run. And after we run the numbers from our graph, boom, we get our answer. The initial rate of disappearance for A was about 2.25 moles per liter per second. That is a huge piece of data. We now know who our suspect is and how fast they were moving right at the start. But remember, A wasn't acting alone. Its disappearance is what caused the appearance of our other two characters, B and C. And that means if you know A's story, we can actually figure out theirs. It's time to follow the trail. This is where our case file, that reaction equation, becomes absolutely critical again. It gives us the ratios, which is a concept called stoichiometry. So for every 2 molecules of A that disappear, 1 molecule of B appears, and 2 molecules of C appear. What does that mean for speed? Well, it means B is created at half the speed A disappears, and C is created at the exact same speed. See? The numbers don't lie. So we can actually use our original graph of A as a blueprint. The story of its decline over there on the left directly predicts the story of B and C's rise on the right. We just have to apply those ratios we just figured out. And there it is, the complete picture. Look at that. You see A's concentration falling, just like in our original clue. But now we also see B's concentration rising up from zero, but only half as steeply. And C's concentration is rising at the exact same rate A is falling. This is the whole story. All 3 of our characters, their journeys mapped out over time. Okay, so we've identified everyone, we've clocked their speeds, we've even mapped their movements. But there is one last really big piece to this whole puzzle, the underlying rule that governs it all. We need to crack the rate law, the secret formula that dictates this reaction speed no matter what. And what do you know, just in time, a new piece of intel comes in from the lab. This table shows data from the same reaction, just run under some different conditions. It lets us compare how the starting concentration of A affects the initial rate. This right here is the key we've been looking for. Let's analyze this new evidence. First, look at the concentration of A. In that second experiment, you can see the concentration was cut exactly in half. It went from 0.105 down to 0.0525. That's a clean division by 2. Now look what happened to the rate when they did that. It didn't get cut in half. No way. It absolutely plummeted from 7.1 times 10 to the minus 5 all the way down to 8.9 times 10 to the minus 6. If you run the math on that, you'll find it dropped by a factor of 8. So here's the puzzle that lays it all out for us. We cut the concentration in half, and the rate dropped to 1/8 of what it was. So we have to find the power n that makes this equation true. 1/2 to the power of what gets you 1/8? And the answer is 3. 1/2 times 1/2 times 1/2 is 1/8. And that tells us the reaction is third order with respect to A. We've done it. We've cracked the code. The rate law is rate equals some constant K times the concentration of A cubed. This is the fundamental rule we've been searching for this whole time. And with that, I think we can finally close this case file. Let's do a quick recap of what our investigation uncovered. So we started with just a single graph, and from that, we figured out it was showing us reactant A. From that same graph, we calculated the initial reaction rate was about 2.25 molar per second. Then, using the reaction's built-in ratios, we predicted exactly how products B and C would behave, and finally, with that last piece of data, we cracked the code and found the rate law. Rate equals K times A to the third power. Every clue led us here to the complete picture of this reaction. We've definitely solved this particular mystery. But you know, in chemistry, there's always another variable, always another twist. What if the catalyst, one of those substances that speeds up reaction without getting used up, was introduced? It wouldn't even be in the equation, but it would change all our graphs, all our numbers. How would that change our story? Well, I guess that's a case for another time.